I'm not seeing the title slide on my screen right now.
No, I stopped sharing so Roger could go ahead and share his PowerPoint.
Okay, well then let me get started. I'm pleased to introduce Roger Bales. Just a little bit about Roger is that he's founding professor of engineering at UC Merced. He's also the director of the Sierra Nevada Research Institute at University of California, Merced. And really importantly for our community is he's the principal investigator for the Southern Sierra CZO and has been since 2007 when the first CZOs were funded. Roger got his BS in civil engineering at Purdue and an MS in civil and environmental engineering at UC Berkeley. Interestingly enough, I learned this today, Roger. He has an MS in social sciences and economics from Caltech.
Yeah.
And that gives me a brand new light on who you are, Roger. And he earned his PhD in environmental engineering science also at Caltech. Roger's a fellow of the American Geophysical Union, the American Meteorological Society, and the American Association for the Advancement of Science. His research interests broadly focus in hydrology and hydrochemistry, and he's contributed greatly to California's efforts to implement policies that adapt water supplies and also ecosystems and the economy to the impacts of climate warming. And so with that, he'll give us this webinar entitled Drought Resilience and Water Security, Observations from the Sierra Nevada.
Okay, thank you so much, Tim and Sarah. I'm really happy to be here to talk about some of what's going on in California. Can you confirm that my slide share is what it should be and so forth?
Yep, you're all good.
Okay, good. Well, Tim, as you discover more things about me, I hope that doesn't mean another committee for the CZOs or something here, but let's focus on California for now. This is part of our critical zone observatory that you see on the screen here, and I'll be talking about how this landscape got to be the way it is, and in terms of the drought impacts and how we can use that for better predictive ability across other parts of the landscape. So what I'm going to talk about in terms of today's seminar, just a very brief introduction to California hydrology. I know some of you know quite a bit about it, but others maybe haven't, and a little bit of the drought history. Then really focus on some of the findings from our CZO, drought in the Sierra Nevada, and then link that back up to water security. So first, California hydrology. Well, in 2011, we had a really wet year. This is Lake Oroville, which is I think the second largest reservoir for storage of river flow from the Sierra Nevada, and been in the news lately. And then in October 2015, the same location. This is just one picture of the drought. There wasn't enough precipitation to refill our terminal reservoirs in the Sierra Nevada for about a 4-year period. Of course, maybe I should be talking about flood today instead of drought, because that's what's been in the news. As you've probably heard, the Oroville Dam, the same reservoir, had the spillway washout and the emergency spillway washout. They're repairing it now. So this is just a little diversion. Then I'll get back to the drought. They decided they needed to concrete this instead of just let water spill over the soil when the water overflows the emergency or bypass spillway. And yeah, they did discover that there may be some weak soil under the spillway at Lake Oroville. Now I bring up floods because, or high flows, which can cause flooding, because that's a key part of water security. So I really want to link floods with the headwaters, with the groundwater, and think of the whole basin perspective when we think about water security. Another picture of the drought is when you look at the snowpack, which is one of our important reservoirs for seasonal water storage. in California. As you know, we have what's called a Mediterranean climate with a wet season during the winter when there's precipitation as rain and snow, and then a dry season. And we depend on seasonal storage to meet the water demands during the dry season. So snowpack typically on an average year, maybe 2010 on the left was more of an average year, stores about half as much water as these terminal reservoirs in the Sierra. At least we think it does, because nobody actually measures how much water is in the snowpack accurately. 2015, you can see things are pretty thin during the drought. 2016 recovered a little bit, still thin around the edges. And then right now, one of the most recent cloud-free scene I could pull was April 3rd. It's a really wet year. The snowpack is about, in the northern Sierra, at least about 150% of average. Precipitation's about 200% of average right now in the northern Sierra. But the snowpack still looks a little thin. Well, these were warm storms, so we got rain instead of snow in more storms than in the past this year. We're already seeing the effects of warmer storms coming in on the snowpack. Okay, this is the only equation I have in this talk. It's a basic water balance, and it indicates the just a water balance on which I'll be using on the study areas that we focus on. Precipitation as rain and snow largely leaves as evapotranspiration with some runoff. And here evapotranspiration refers to evaporation, sublimation, and water use by vegetation. So a little more introduction to California hydrology. I turned the state on its side here so the water will drain out to San Francisco Bay from the Sierra Nevada and Central Valley. No, really, just so I could fit it on the slide better. But if we go on the bar graph, you can see going from the Kern River in the south to the Feather River in the north, the total height of the bar is precipitation. And as you can see, precipitation increases by at least a factor of 2 as you go from south to north in the Sierra Nevada. And P minus Q, which is an index of evapotranspiration, precipitation minus discharge measured at the terminal reservoirs, doesn't vary that much across the Sierra Nevada. We have about the same amount of evapotranspiration, which varies not based on the amount of precipitation, but really on the elevation of the basin. So I'm going to be focusing mainly on the Kings Basin here in the Southern Sierra. One of the Kings and Cahuilla have the lowest evapotranspiration. They're the highest elevation basins in the Sierra Nevada. Now, a statewide water balance. Here, in the upper right, I indicate total statewide precipitation, which is on the order of 200 million acre feet. Sorry for using the common units, but that's what we buy and sell water in California and in the US. Some say it's about 220 million acre feet. We don't, on average, we actually don't know how much precipitation occurs across California because we have very few measurements in the Sierra Nevada. Then the applied water use is about 80 million acre feet, and that's the circle in the middle of the diagram. Where's the rest? Well, the rest either stays in the headwaters and goes out as evapotranspiration, or it may run off directly into the ocean. Then of that 80 million applied water use, about half is for the upper part, which is environmental flows and in-stream uses and so forth. And the bottom half is our developed water supply. So when people say 80% of our water supply is for agriculture, they're talking about the fraction of the bottom half of the circle that goes for agriculture. Now, if you follow the news on water conflicts in California, the agricultural community is always making efforts to shift water from the upper part of the circle to the lower part of the circle, from environmental flows to agriculture. My position is they should be looking at the number in the upper right and look at why the applied water use is 80 instead of 81 or 82 million acre feet. And we'll come to that in just a second. Okay, that's a little background on the hydrology. I want to touch a little bit on the drought history. This is what this American fire. This is what's happening to our forests in the Sierra Nevada as we get hot, dry conditions. That is, stand replacing wildfires rather than low intensity fires. Okay, these are the drought indices from the downloaded from University of Nevada. University of Nebraska, excuse me, Lincoln. You can see on the left, the last wet year was 2011. And the drought started basically in fall of 2011. It increased to progressively drier conditions through 2015. Then we started to get precipitation during winter 15-16. It decreased in intensity a little bit. And then the most recent drought index shows only Southern California still experiencing moderate drought conditions in the South Coast area. So when it was interesting in the newspapers this week, the governor declared an end to the quote drought emergency, but the newspapers shortened it to say the governor declares an end to the drought. And there's a difference here. California still has dry conditions in parts of the state. One last thing on the drought record. This recent 4-year drought is not an anomaly. This is a graph that goes from time, four panels go from the year 900 through the early 2000s. And the pink line, or horizontal line, indicates the average river flow for the San Joaquin River, and the annual values are shown as a black line above or below that. Shaded in pink are the below average periods when the San Joaquin River flow was below average for 4 years or greater. So you can see that there's at least 1 and up to 6 of these 4-year or longer dry periods per century. And that's really not been factored into our water resources resilience in California. These data from the Arizona, the Tree Ring Lab. Okay, let me jump over a little bit to talk about what's going on now with the drought in California. Again, these are photos from near one of our research sites. Let me jump back to the longer term experiment. I like to call it an experiment that's going on in the Sierra Nevada. And the left-hand panel is a photo taken from 1896, showing a forest density in what is thought to be an undisturbed forest, that is lack of logging or human influence at that. And the panel on the right shows about 100 years later, the same location. Visually, one can see a higher forest density. When there was mining started in California, there was concern about fire suppression to protect the assets of private property. As time went on, people started living in the mountains and developing other commercial activities in the mountains, and the pressure for fire suppression got higher to protect private property. And you remember, some of you may have come to the CZO all hands meeting that we had up in Fish Camp in the Sierra Nevada near Yosemite at Tenaya Lodge. Tenaya Lodge wouldn't be there if there wasn't fire suppression in the mountains. So we enjoy those benefits. So when Congress mandated fire suppression, fire was a natural part of the landscape. When they mandated fire suppression, biomass density increased in the mountains, and we're now seeing the results of that in our water balance, our fire intensity, and many other changes in ecosystem services. So I'm going to give a few results from our research at the Southern Sierra CZO. Basically, we're looking at the response of the Southern Sierra water cycle to drought. That is the shorter term experiment. On top of this longer term fire suppression experiment, we have the short term experiment of what happens when you reduce the water coming in as precipitation. So this is part of our broader research program to try to understand how did the forest get to be the way it is. It's coped with dry periods, extended dry periods for decades since the fire suppression started, and before that at lower densities. Is this a new pattern, or is this part of a natural cycle? To what extent is this driven by the increases in temperature, for example? And how does regolith water storage and other factors buffer the drought? So we'll look mainly at the response to drought right now. Again, just a little bit of what's going on in that near our soaproot saddle site, the pine oak forest. So data I'm going to show today come from our measurement sites, and we hypothesized different levels of regolith storage going from the oak savanna, where it's less weathered due to drier conditions, up through the pine oak forest, where you see well-weathered material, up through the mixed conifer forest, and then up into the Salba pine forest that's cold limited. The rain-snow transition is somewhere around the mixed conifer forest or slightly below that, where it's 50% rain versus snow. Our field measurements, this is in the upper right, shows a MODIS image going from the 4 dots there, going from left to right, are the oak savanna, the pine oak forest, which we call soaproot saddle, and then the mixed conifer forest, which we call Providence, and Shorthair Creek, which is higher, definitely in the snow zone. The problem is I don't have any data from there, but the drought impacts were minimal there during the period we're looking at, because we don't have data because a tree fell and knocked the tower out. And it's back up now, but we don't have that early drought data from there. So I'll have data mainly from the middle 2 sites, also the San Joaquin site for comparison. And these started reporting in 2009 to 2011, depending on when we started, depending on the tower. So let's look at some data from these sites. This is cumulative water year evapotranspiration, water year from September 1st through October 30th. On the top panel is Providence, the mixed conifer forest, where we saw about a 20% drop in evapotranspiration, mainly in the last 2 months of the water year, between 2011 and 2014. Versus the pine oak forest down at Soaproot Saddle, we saw almost a 50% drop in evapotranspiration over the last basically 4 months of the water year. And I put for reference the 2016 data on here showing that evapotranspiration actually dropped further. It did not recover after we got a wet year. Providence did recover to closer to 2011 levels. Now, it's nice to know that out of sight, but we really wanted to scale that to the whole Kings River Basin, 3,900 square kilometers or something like that, in order to understand the water resources impacts of this. So to do that, we use this scaling relationship that my colleague Mike Goulden developed, where each of these dots on the upper graph in the upper right is the measured evapotranspiration from a flux tower in California. I think they're all California, maybe some outside the state, and the MODIS Greenness Index, NDVI. Pretty tight relationship here. So we use this relationship then to calculate the evapotranspiration across the full landscape. And this makes sense because, high leaf area index is gives us high evapotranspiration, primary productivity, and so forth. And NDVI then indicates the evapotranspiration that the vegetation needs in order to stay green. So it is a bit of a lagged indicator because it takes a little time for the vegetation to actually turn from green to red when it's stressed. When we do that scaling in the Kings River Basin, we see high elevations, high Sierra, lower evapotranspiration because it's cold limited. We see the middle elevations, really high values approaching 1,000 millimeters per year. And then the lower elevations, the oak forest, again, these are water limited, so they show lower evapotranspiration values. So we have, I think, at least for annual evapotranspiration, a good scaling procedure here. Now, when we divide that up by elevation band, I've got two panels here before the drought. So on the abscissa, you see elevation in thousands of millimeters going from the oak savanna up through the high snow zone. Below the zero line, I've plotted evapotranspiration. So you can see evapotranspiration is highest in the basically 1,000 to 2,000 meter elevation range. That's the so-called happy zone for trees where it's not too cold and not too dry. The total height of the bar on this left panel is the precipitation in that elevation zone. And we used as an index of precipitation, we used the PRISM data. Then when you subtract the evapotranspiration from that PRISM estimate of precipitation, you get the blue bar above the zero line, and that's the estimated runoff for this 4-year average before the drought. Now let's go to the same picture during the drought. Again, below the line is evapotranspiration, but how did the evapotranspiration stay so high in the elevation zones with less precipitation than evapotranspiration? Well, the answer is there was multi-year storage. So the red shaded bar on the right-hand panel shows our estimated amount of the evapotranspiration that actually came from storage. And just based on this mass balance, there was no runoff at the lower elevations. It all came from basically the snow zone, what runoff there was, where evapotranspiration is more cold limited. Of course, you know what happens as the climate warms. That cold limitation diminishes. Now, we confirmed this multi-year storage availability and depletion with several lines of evidence. I'm just showing one here. This is matrix potential measured at a 2-meter depth at those two sites, the Providence site, which is the mixed conifer forest that didn't show so much drought effect, and the soaproot that did show the drought effect. We see over time a progressive decline in the matrix potential at soaproot, and the start of a decline the last year of the drought at Providence. Basically, there wasn't enough precipitation to recharge below about the top meter at soaproot. And so when the halfway through the summer, when the forest growth used up all the water in the top meter, the roots try to tap into the second meter, and there's no water there because it didn't recharge during the drought. And the result was a decrease in evapotranspiration. Now, looking at the scaling of that to the whole river basin, I've put more years on here, 2005 through 2015. I guess I don't have 16 on this graph. Again, the same sort of plot, evapotranspiration below the line. Now this is whole basin, like whole Kings River basin. You can see that withdrawal from storage, multi-year storage, is a relatively common phenomenon based on the mass balance in these lower elevations. Now we're comparing the stream flow, or the runoff rather, estimated by taking the prism precipitation minus the flux tower and MODIS estimated evapotranspiration to give us the blue bar above the line when I sum all the elevations together. And wow, that pretty well matches the estimated full natural flow. That is the measured stream gauge at the on the river plus estimates of diversion. So we think this is another good closure of the water balance at this basin scale based on the measurements that are available here. So P minus ET minus delta S in the upper right-hand panel is basically our runoff and the full natural flow, and they pretty much follow a one-to-one line pretty well for this time period. Okay, I should say that the yellow circles are a little bit different because that reflects maybe some going to or from storage. So their interpretation is that the regolith storage was sufficient to buffer drought in areas where there was sufficient mean annual precipitation. But the decline in evapotranspiration during the drought is where recharge to the deeper root zone was limited, suggesting that parts of the Southern Sierra really have reached a tipping point in their ability to be sustained through hot multi-year droughts, and we expect this effect to move further north in the Sierra Nevada as these drought events continue. In the picture here, you basically see most of the conifers are dead. You have the oaks and the shrubs remaining in this pine oak forest. So where are we headed next? Well, we want to predict where forests are resilient versus vulnerable using multiple estimates of regolith storage from field surveys such as the seismic refraction and other field surveys that we've done, and apply different climate scenarios besides the 4-year drought that we had here, evaluating the vegetation density and the amount of evaporation that really can be sustained over time across the Sierra Nevada. There are active efforts to thin the Sierra Nevada forests. You can see in this picture, this is really the only area that I have in the Sierra Nevada where I have a picture, and I think the only one where it really is, at this point, a restoration thinning. The foreground is closer to the vegetation densities that existed 100 to 150 years ago, or 100 years ago based on surveys done in the early 1900s. The background is the current forest density. This photograph's taken a little further north in the Stanislaus National Forest. So there is a management response, but the pace and scale of forest restoration is pretty slow right now in California. Let me just make a few comments applying this more broadly to water security across the state. I like to talk about, when I think of water security in California, I think about the 3 I's: infrastructure, institutions, and information. Infrastructure is our, not only our dams and canals and so forth, but it's also our headwaters, our green infrastructure, and our groundwater recharge basins and things like that. strong and more adaptable institutions, we're trying to move, or at least the state is trying to move, to more whole basin management of our water resources. That is, can you imagine what we could do if we were managing the headwaters and the groundwater as a connected unit, rather than being disconnected by dams and rivers in between, which are so 3 different management strategies there. But we really put better and more accessible information as the foundation of that, and water managers in the state recognize that we've got to move beyond using technology from 50 to 100 years ago and upgrade the amount of information coming in to resource management. And water security lies at the heart of adapting to climate change. So a little bit of the history of California here and how we got to the situation we're in now. In the pre-statehood era, that's when we think the forests were at relatively sustainable levels, experiencing low intensity wildfire either from lightning strikes or the Native Americans who lived in the forest. During the development and growth period, the resource extraction period of the state, our headwaters started degrading. Then we had the federal investment and state infrastructure investments in our dams and reservoirs. Then entered the era of, in the 70s, we remember the major environmental legislation came into place, but it was also a big era of conflict on water in California. Now, this is from the state water plan. The state optimistically says that we are entering a period of sustainable resource management. There's bond funding, although not yet bond funding, to restore our headwaters. I question how far we actually are moved into sustainable resource management. There are lots of debates going on, but we've really got to get there. And I think findings like I just showed you really can help that debate, or are helping that debate in the state, and changing the nature of the debate to be based more partly on science rather than just on politics. The state passed the Sustainable Groundwater Management Act, which actually could, if implemented the way it was intended, force the management of resources from headwaters through groundwater based on actual mass balances, water balances in the river basin and including the groundwater. So our big questions there: are we going to deplete our groundwater or sustain it for future generations? What's the level of sustained supply that we're going to maintain? And how do we make up for storage that we're losing in the Sierra Nevada as the climate warms? Remember that the large water use is for agriculture in California, and we won't go into the water rights structure right now, but just to say that the demand is offset from the supply. And a final graph, or my other final graph that I have here, I just wanted to point out, if you go through the water year from September 1st in the fall through winter, spring, summer to the next year, you see the blue line, the upper line on the left, as being the approximate typical runoff for a Sierra Nevada watershed. It peaks in the early spring and then declines. The water demand, of course, peaks a few months later. So the area in between is our water to storage and from storage. We can't use all of the reservoirs' capacity for storage because of the required flood releases. And there's a gap here. Projected conditions as the hydrograph or the runoff shifts to the left. There may be some shifts in the demand curve also, but as was brought home this year in the operating Oroville and other dams, the required flood releases are increasing in a warmer climate. That is, you got to have more storage capacity for big rain events, because those big snowstorms are going to be rainstorms. going forward. Meaning that the shortage, how are we making up our shortage now is to overpump our groundwater by about 2 million acre feet per year on average. That shortage has to be made up some way else in the future. We can offset that a little bit if we implement additional storage, such as groundwater recharge, where floods and drought come together. Can we overpump the groundwater during drought, and then by cleverly diverting some of the flood flows onto ag land and other areas, recharge the groundwater? And the answer is yes, it's technically feasible, but we don't have the infrastructure in place to do that. So again, putting infrastructure, institutions, and information together, we can achieve water security. And I think our findings I've showed you on the headwaters are a key piece of that. So just a summary, whoever can identify where this picture was taken, maybe I'll buy you a beer when we get together. This is, we were doing some recon for another flux tower at a higher elevation, I'll tell you. So management relevant science, high evapotranspiration across a wide swath of the forest, higher than was typically projected from previous hydrologic modeling in the Sierra Nevada. Higher water yield and resiliency in the snow zone. Sustained forest management is what among the many infrastructure repair and investment needs, and better information is critical going forward. And acknowledgements, if anybody in the audience was in this picture, let me know. This was during one of the drought years. Right now, well, not right now because the snow was warm, but during the peak snowpack, water was over these people. I mean, snow was up to these people's heads or above at our mixed conifer CZO site. Thanks for your attention, and I will be happy to take questions.
Thanks, Roger.
Thanks, Roger. So everyone can unmute themselves now. We ask that you just stay muted when you're not speaking.
Roger, this is Tim. Can you hear me?
We still good?
Can you hear me, Roger?
Yeah.
Okay.
Yeah.
So I think I followed everything. It was a great presentation. Some of the science is beyond me, but I'm wondering. I'm trying to put together some of the history you told us with the present, and it seems to me that if sparser vegetation is the norm, then the ongoing die-off or the thinning of the forest is getting things back closer to normal. I'm saying normal with quotes, and that would have then. That might have a positive impact on groundwater recharge and runoff, surface runoff. Is that reasonable to think?
Yes, with regard to evapotranspiration, it is. But there are other ecosystem services that the Sierra Nevada provides, and those may not be optimized by a stand replacing wildfire. Such as habitat and the stand replacing wildfires. Well, let me go back to the drought. Yeah, the drought situation is reducing the evapotranspiration, about 60% by the end of the drought at that one area. That is closer to a sustainable level. Whether it's the norm or not, I'm not sure. We haven't investigated that. But yes, but it's the pattern of forest thinning that one wants to optimize for forest health. And I think the sort of thinning that is useful for lowering the wildfire risk is also one that can achieve goals of taking the evapotranspiration closer to historical levels, or in fact, we may have to go below historical levels for a sustainable forest at this point because of increasing temperature.
So in a sense, you could log your way out of water, out of the water issues you have in the state. I'm sort of saying that tongue in cheek, but it could play an important role.
I'm not sure if people here in California would use the word log, because it's basically stewardship contracts to remove all the small trees that don't have much market value. Even though the biomass is about double what it was in the early 1900s, the number of trees is about 6 times on average. So the mature forest of 100 years ago or so was a small number of large mature trees. The current forest is a zillion small trees.
I got it.
Yeah, oh, Paul Brooks identifies himself leading the pack in this picture here.
This is Tim again. I have another question if no one else does. Just if anyone has a question, just interrupt. So I'm wondering, just sort of bigger scale. It's my impression that a lot of the, like some majority, I don't know if it's 40% but a large portion of the overall water supply for the state is groundwater, and that a lot of it is used in the Great Valley for ag. And I'm just wondering, conceptually, do those aquifers get recharged mostly by surface flow down into the valley and then flooding, or are there groundwater connections from the High Sierra flow as groundwater that make it down into the Great Valley?
At this point, most of the recharge in the Central Valley is from percolation below the root zone of irrigated fields. There's quite a bit of recharge at the mountain front where the rivers come down, if you can slow the water down. But during the mining era, a lot of those rivers were channelized. But the state there have been a couple of cases where the levees have been moved back away from the river channel to try to increase the size of the floodplain. So it's mainly the ag lands where the largest amount of recharge is occurring. There is some subsurface flow out of the mountains into the valley. It's thought to be small. It's really not been estimated. It's a research area and a research need there. So the thought is, where the investment is looking for, you can flood these almonds, walnuts, and so forth, pistachios, for a short period of time and not in the spring or early spring, late winter, and not damage the crops. You can do the same to orchards and so forth. So it's trying to use more of the land as recharge, but also remember we have a long-term structural deficit on the groundwater in the Central Valley, which means you either have to take land out of production or use water more efficiently, or shift the evapotranspiration from the Sierra Nevada down to the Central Valley.
Huh.
I don't know if I answered your question, but I said what I wanted to.
That was very clear.
Yeah.
Hi, Roger. It's Huria Drami from UC Rivers.
Oh, hi. Glad to see you.
I have a question about the storage region. Do you think is the local storage, or probably someone contributes to fill up the storage in the lower elevation so it can
Huri was breaking up on mine. Tim, did you hear that? Did you repeat it? Or?
I did not. It broke up a lot for me too.
You can try again if a shorter question, Huri. That broke up a little too much to get your main point.
Okay, sorry, I try again. So I'm wondering about the sources of storage at a lower elevation. Is it the local storage or water that comes through the bedrock from higher elevation?
Yeah, okay, so
Yep.
we even up in our headwater catchments where we're monitoring, we're not catching all of the flow out with the stream gauge. There is subsurface flow going out of those basins. We don't know where it reemerges into the river. If it does, we know in some rivers, there, from Martha Conklin's work, that there is subsurface water from higher elevations coming in to the, say, the Merced River in Yosemite. So there are these subsurface flow paths, but I don't think anyone has really made credible estimates at the river basin scale of how important they are on the whole water balance. The soil moisture storage, let me say regolith water storage, let me just think of that as being mostly above the groundwater, has historically, I think, been about equal to the snowpack storage. And so the two together provide as much storage as all the rim dams there. So I guess I'm saying is, why don't you help us figure out how much of this regolith storage is taking subsurface pathways versus re-emerging into stream channels down below in the Sierra Nevada. I think that would help, because there have been claims made in the Central Valley that people have a great subterranean channel coming onto their land, therefore they can pump as much water as they want.
Mm-hmm.
Now that may be true in the Kings River Fan, but I don't think it's true in the Merced River Basin. But again, that needs to be investigated.
Okay, thank you.
Any other questions? If you want to ask a question, you need to go to the lower left-hand corner and unmute.
Well, Cliff's guessing that that's Mount Tom in the background on this previous picture, but I don't. It's actually not Mount Tom. It's a little further south than Mount Tom.
That square mountain right there is definitely Basin Mountain.
Okay.
And the one, right? Isn't it?
Well, just over the near ridge where the cars are parked is Parcher's Camp, South Lake.
All right. Well, I'm confused by the perspective, but I thought that was Basin Mountain in the background there.
It should be Wallace and Heckle in there. And I forget what else. I'm drawing a blank on names. I forget the names because I don't go to the High Sierra as much as I should these days.
All right, well, if there's no more questions, let's finalize this event. And I'll remind everyone that we'll have another webinar in 2 weeks from now. And thank you for attending. Thanks, Roger.
Thank you all for attending. Yeah.